Hi, this is Jeff Spence, your Math 135 instructor for the Community College of Denver. We're moving on to 6.6, which is applications of the normal distribution, standard normal distribution. So, in the last classwork, we were just working with the standard normal distribution with z-scores, finding area from z-scores using normal CDF, or if we have an area, we would use inverse norm to find a z-score. So why would we do all that stuff? Well, it's all about these real-life applications. There are a lot of real-life data sets that follow the normal distribution, that have a bell shape. The most classic example is the heights. Another one is the SAT. The scores on the SAT are normal, which means that we have a bell-shaped curve. Okay, normal with a mean of 500 and a standard deviation of 100. So that gives us this picture here where we have the normal curve and the mean, 500, goes in the middle. Standard deviation of 100. Now we don't need to count that off or anything, but we should jot down that the mean is 500 and the standard deviation is 100. Okay? And it says find the probability that we score at least 615. So for some reason, for a certain college, they need you to score 615 on the math portion of the SAT. So 615 would be somewhere over here on the right, 615. And we need to find the probability that we score at least 615. At least means that or above. So when we find this probability, we're looking for this area. That's the answer that we're looking for, that area. Well, that's why we would use the standard normal distribution, because sometimes if I want to do a similar problem with heights, I need to standardize this by doing a z-score. I need to figure out how many standard deviations 615 is from the mean. So what we do, we compute a z-score. So I'll do that right here. I say z equals 615, the data point, minus 500, the mean, over 100. Do that calculation and you get 1.1 gosh, it's really bad at decimals, 1.15. Okay. Now, we know that this 615 is 1.15 standard deviations above the mean. So we know now it's, as far as the z-score, is 1.15, and we're back to 6.5 now. We just need to find the area to the right of a z-score of 1.15. So that's as simple as doing normal CDF. The left endpoint would be 1.15, and then the right endpoint would be E99. Type that into your calculator, and rounding to 4 digits, we should get 0.1251. So in other words, there's a 12.51% chance that we're going to score at least 615 on the SAT. That's why we use the standard normal distribution, because there's all types of distributions. We could be asking about heights, SATs, weights, times. We need to standardize every score and then use the normal CDF to find area. Okay, so now we're on to an example with men's heights. Men's heights are normally distributed with a mean of 70 inches and a standard deviation of 3 inches. Find the probability that if we randomly select somebody, they're at most 75 inches tall. So remember, normal tells us that we can draw the bell curve and put the mean in the middle. A mean of 70 inches. Okay? And then the standard deviation is 3 inches. Let's jot that down. Mean 70, standard deviation 3, because remember, we're going to use this for our z-score formula. And it says, find the probability that a randomly selected person is at most 75 inches. Well, 75 is definitely more than 70, so 75 goes on the right side there, And it says, find the probability of at most 75 inches. Remember, at most is up to that number. So we're actually asking for all this area to the left of 75, at most. Okay, so this whole area here. But once again, in order to do this area, we have to know the z-score for 75. We have to know how many standard deviations away from the mean, and then we can use our normal CDF. So we have to standardize it. So we do a z-score. We do z, I'm going to move it, I like to do it down here because these are below. Z is 75 minus 70 over 3, which turns out to be 1 point, if we round that to 4, equal to 1.6667. All right, then we need to find the area from the z of 1.667 to the left. So that would be normal CDF of negative E99 to 1.6667. Enter that into your calculator, and if we round that to 4 digits, we'll get 0.9522. So there's a 95.22% chance that if we randomly select the male, he'll be at most 75 inches, so 75 inches or less. Okay, on to some further examples, but these examples now we're going to do where we have an area and we're going to have to go back and find a score. So let's go back to the SAT math. The SAT math is normal with a mean of 500 and a standard deviation of 100, which means that we can draw the normal curve. Put up our curve there. Put 500 in the middle. And do the, that looks like 560, 500. Okay. And we need to find the score that represents the 75th percentile. Remember, percentiles mean a ranking that if you have the 75th percentile, that means that you scored higher than or equal to 75% of the rest of the people that took the test. So that score has got to be somewhere over here on the right, such that the area here is 0.75. That's what that means. That's what the 75th percentile is. 75% below you. So I'm drawing an area of 75% to the left. And we need to figure out this x value. So these are backwards problems. Well, to start, we're going to use inverse norm. We're going to do inverse norm to figure out what z-score has an area to the left of 0.7500. So if we do inverse norm of 0.75, we get 0.6745. That's the z-score. So now we know that the z that corresponds to a left area of 0.75 is 0.6745. 0.6745 standard deviations above the mean. So now we know the z and we have to find the x. This is the formula we've used before where we find the x. We do x is equal to the mean, which is 500, plus the z, 0.6745, times the standard deviation of 100. This x will be, let me see here, 567.45. I hope I did my math right. Okay, so a score of 567.45 represents the 75th percentile. If you score at 567.45, you are at or above 75% of the rest of the people that took the test. Okay, last example here. We're going to stick with the SAT with the mean of 500, standard deviation of 100. So it's normal with that parameters. We're still using those same parameters. So 500 goes in the middle. This time we're going to ask, find the score that represents the cutoff for the top 10%. The cutoff for the top 10%. Well, the top 10% means the highest 10%. So we're talking about 10% on the right. So this score has to be somewhere over here. And we know that this 10% is over here, the top 10%. 10% as an area is 0.1000. Okay? And we need to figure out this x value that represents the cutoff for the top 10%. You score above that, you're in the top 10%. Well, we got to go through a z first. And to do a z, we have to do inverse norm. But inverse norm only knows left area. So if 10% is on the right, then 90% must be on the left, which is an area of 0.900. So we do inverse norm of 0.9000, and we get we get 1.2816, which means that the z-score that is the cutoff for the top 10% is z equal to 1.2816. So to find the x, once again, we go through our formula. X is the, let's see here, what color is it? Purple. Okay. X is the mean, which is 500, plus the z-score, 1.2816 times 100, the standard deviation. Plug that in, and we get 628.16 as the score. So if you score above 628.16, you are in the top 10 percentile. That is the cutoff for the top 10 percentile, this answer, the SAT score. So we've done examples back, forward and backwards. If we looked at the original one, remember, the reason we did all that z-score stuff in 6.5 and finding areas is because there are real-life applications that are normal, standard normal distributions. We use their mean and standard deviation to find the z-score for any x value, and then normal CDF to find the area or probability. On the last two examples, if we know the area or the percentile, percentiles and top 10% are just areas. Okay, percentile always means area to the left. Top 10% means area to the right. We do inverse norm to figure out our z, and then we go back and use the x formula to figure out our data value. So that's the examples that summarize 6.6. Make sure you go over this many times, and good luck.